Alrighty. So we're going to go ahead and pick up from where we were at the end of class last time. So we were looking at this data set here called wages. And just as a quick refresher, we can look at what is contained in here. 6 different columns. The one that we had been interested in setting as our response variable, so regressing earnings against characteristics of the individual. So height, sex, race, education, and age. Height, education, and age are our numeric variables. And so these are typical sort of continuous variables, height indicating inches of height, education indicating years of education, and age for how old the person is. And then we also have sex and race. So let me see. We can look at, for sex, you've got 2 genders, and for race, we have unique, wages, race. We have white, other, Hispanic, and black. And so these fall under the 2 categories of variables that we were discussing last time. You've got a dummy variable and a categorical variable. So when we think about running these in a regression, right, we understand how if it's a number, we know how to relate that in terms of measuring some kind of slope and looking at the correlation. But if it's a dummy variable or categorical variable, what exactly is going on? And so let me go ahead and go to a whiteboard. So one way to think about this, so if I were to sort of write out the table, we have something that looks like this. So earnings, and then perhaps we have age and gender. So you'll have a bunch of values here, and you'll have a bunch of values here, and then you have male, female, something like this. So essentially, we need to be able to turn this into some numeric representation that you'd be able to actually do the regression on. So what is effectively happening behind the scenes, which I didn't show last time, is that by characterizing this variable as a factor, you are coding specific values to each entry here. And so effectively, I think the best way to think about what's happening behind the scenes, even though you don't see it, is that you have something like this. You end up getting 2 extra columns that will end up looking like this. And then you are essentially running a regression against all but one of the gender variables. And so let me explain what I mean. When we reformat the data to kind of look like this, it turns out that you can realize that a dummy variable where you have 2 sort of options, binary 1 or 0, is going to end up looking as exactly the same, essentially a subset of categorical variables. And so what I mean is if I go ahead and delete this stuff, and instead we take a look at our categorical variable, the organization kind of follows the same logic. So here, let's do race. So you might have white, white, black, Hispanic, other, something like this. And the way that R treats this would be much in the same way, right? So white, black, we'll just say other for O, and H for Hispanic. So you would have something like 1, 1, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, and so on. So this is essentially what's happening as you define a variable as a factor, and then the regression will be doing solving the for the slope exactly in the same way, treating these values as ones and zeros. I had briefly mentioned that you would choose any combination of 3 of these to be represented within the regression. And the reason for that is you have, you'll end up having what's called a singular matrix if you include all of them. And so you have too many degrees of freedom. And you'd be able to essentially perfectly explain all of the variation within your race. So that's technically not something that you'd be able to represent mathematically. So you always have to drop, or you're essentially representing the extra variable via the intercept term in your regression. So we'll show what that means in our example. So let's hop on back here. So in this case, if I run a regression against education, age, and gender, you'll notice again that there is only a single gender term, and the intercept actually is the thing that represents the other factor. So our base level in this example is for female, and then males make this much more. In fact, if I were to do a simplified model, essentially would look something like this, where I'm just regressing against gender. And we'll see what this looks like. Oh, wage gender model. Essentially what this is going to look like is it's saying that across my wages, or across the genders, on average, females make 24,246, plus or minus some amount in your standard error, and then males on average make 21,748, plus or minus some amount more than females do. Okay, and in fact, if you wanted to change the baseline from male to female, you could actually code that in to the data. So the way that you would do that, and so this makes no influence on the actual results of the regression, but when you display it, it will show via a different baseline, which can be useful if you want to set something to a specific baseline. So this might be something like, oh, not race, gender. So I want to re-level, it's writing the wrong variable here. So sex, and the reference I want is male instead of female. So by default, it actually just goes by alphabetical order. So F becomes before M, but if we re-level it, let's see. This is only for unordered factors. I see. I guess there's already an order set. So if that's the case, I think a different way you can do this is like this. So factor, and it just depends on the order that you do. So this is the same thing that we learned before about how to create factors. So I'm redefining the factor and I'm setting the level of the male first. And hopefully this works. I'm not 100% sure. Okay, yes, it does. So in this case, it's saying on average, a male makes 45,993 and a female makes 21,748 less. And we can see that this number is exactly the same as when we had a female as the base, but it's just going down instead of going up. Okay, great. One way to, let me see if it's, if I can sort of draw this out. So if we think about this qualitatively and what the effect would be, it would essentially look something like this, where for my wages, and I have some spread of data, essentially you would have a flat line sort of for male and for female. And these are representing the actual level that's specified by the coefficient. So for the male, this would be about 45,993, and then the female would be 45,993 minus 2,178, which we actually know the number because we ran it the other way. So it would be 24,246. So just we're going to go through a couple different structural or a couple different specifications. So kind of keep this in mind. In this first example, it's sort of just these flat horizontal lines. Okay, if we were to go back to our initial model where we include education and age, actually I can go ahead and draw this one as well. So if we were just doing something like age, the relationship is something like with age, you have a sort of positive line. So as you get older, you are essentially making more money. So it might look something like this. Now, as you throw in the factor, you are essentially creating a new intercept point. And so where we had kind of a flat line before, a flat horizontal line, now you have two lines that might look something more like this. So you have female and male. And so if I go ahead and run this summary, so in this case, if we're looking at age, the rise over run would be 281. So for every additional 1 year of age, it equates to about a $281 increase in your wage on average. And that's the same for whether or not you are male or female. But if we look at the intercept, then the female would start at a negative 47907 salary, and the male would start at negative 47907 plus 21,000. So it would be, let's see, negative two. We're going the other way. Plus 27907. Is that right? So 26907, something like that. So in this case, you now have two lines which are representing the different levels for male and female. Okay. In this particular example, one of the things that I want to do is just show kind of step by step the diagnostic process that some of the things that we had already talked about. So I can look at, for example, the level of significance among the different variables, which seems all pretty reasonable. R squared is kind of low, but for more of a diagnostic about the model, definitely one of the things I want to look at is the residuals. So I'll plot that, and one of the things that you'll notice is that, okay, so there's some kind of heteroscedasticity, which refers to the fact that maybe the errors are sort of kind of growing, right? So if you look at the spread here compared to the spread here, it looks kind of different. So that's not so unusual, and there are ways of dealing with that. But probably more concerning is I noticed that there's kind of this like line down here. So that's not so uncommon to see in residuals. And typically, if we think qualitatively about why that would happen, it's essentially saying there's some kind of like cutoff that's happening that looks weird on one side of your fit line. And I can tell you, I guess from experience, that typically means you have a sort of data cutoff. And typically that comes from something like, in this particular case, there's a pretty obvious reason for that. And that's having to do with the fact that you can't actually have negative wages. And so there's nothing in the data where it's below zero, whereas the fit might have a line that's going into your negative. And so so you'll sort of always have this a sort of minimum point at any prediction level, because you can't go beyond, because you never see points that go beyond zero. And so one thing that we commonly do to get around that is a transformation where the response never has any ability to go below zero. And so the way that they do that is just to simply do a log. And so we can do that here. So I'm going to run the exact same regression with a log, and then we can take a look at what that looks like in terms of the results, as well as if it helped at all with our diagnostics. Okay. So let's take a look at our results. So now this looks a little bit different. If you'll remember from last time, the way that we interpret this is now slightly different. Because you have logged your earnings, we can essentially say the response here is essentially saying for every additional year of education, you are increasing your earnings by 16%, and for every additional year in age you're increasing your earnings by about 0.89 or 0.9%. These guys are a little bit less intuitive to interpret. You'd have to essentially just do the conversion from the log in order to be able to interpret that. In this case, our residuals look a lot better, especially with respect to the heteroscedasticity, but you still have some issue with these cutoff points. And so I won't get too much into this, but you can sort of dig around and look at some of the data and see what's inappropriate. What ends up happening is actually you get some issue with really low wage earners essentially biasing the model. So just in order to I'm not talking about how we get there, but just in order to look at the residuals, we can see what happens when I filter some of these guys out and run the model. Then you have sort of a more proper residual plot that looks a lot more reasonable and would be something that you would think is probably a little bit more robust, especially in terms of going through some of the diagnostics. And you know, again, it's always good to look at many of these tools, because when we simply look at the standard errors or the R squared, you may miss some of this issues in the bias in the model. That's definitely evident by looking at the residuals. And if we look at the model, we can see whether or not if there's any sort of significant difference in the interpretation when we cut out those points. And indeed, your coefficients are changing by actually larger than the standard errors here. So this was 16% 16% plus or minus, right, 1.4% per standard error, whereas here it's a little bit lower. It's 12.3%. Okay, and so that is kind of a way that we can, or a quick example of showing some of the stuff that we've learned and walking through to try and step by step fix the model. Okay, so we can continue on to one more topic. So let me switch over to the whiteboard. So one more topic related to this. So we've talked about dummy variables and we've talked about categorical variables. And the last thing that I'll talk about is interaction variables. So this is a relationship among 3 or more variables if the influence on the third is not additive. Okay, so this might look something like this. So if we have our typical regression equation, suppose we have 2 variables. Oops, I jumped ahead here. And then suppose that we think that there is a relationship between the 2 variables that we have in our model already. So this might look something like this: b1 or b3 of x1, x2. Okay, and we also have our error term here for our i's. So we are talking specifically about this term, and so this is an interaction between my x1 and my x2. Okay, what the heck does that mean? So we've talked about, so just as an example, so we've talked about for our wage, you have male, female, and then we've looked at something like for age and wage, you may have some relationship that looks like this. And then you may have also wage and age and a differentiation between male and female here. So this would be y equals beta gender. This is y equals beta age. This one would be y equals beta gender plus beta age. And now you might think to yourself, well, what if the slope between male and female for age is different? So that's referring to maybe something that looks like this. And so now we basically have our 4 examples here. And we've looked at the first 3, and the last one would be something like y is equal to beta gender plus beta age plus beta, oh, okay, I'm running out of room here. I'll write it above in a different color so I can just overlap. So y equals beta gender plus beta age plus beta gender times age. Okay, and so we can quickly go back to our example to see what this looks like and sort of how to interpret this. Okay. So the 4 examples look something like this. Okay, I was using age instead of education, so we can replace this so it'll be the same. So wage model 1, earnings against gender, earnings against age, earning against age and gender, and then in the final one, looking at earnings against age, gender, and then age interacted with gender. So let's go ahead, go on all of these guys. I know that, you know, we've identified some of that bias from the residuals before, but I'm kind of just ignoring that for now. We'll just look at the interpretation of these models. So here we've looked at this. So this is just the flat lines for gender. This would be just the slope for age, saying, you know, every year you're older, you on average make $147 more. Here we have both age and gender. So the slope is actually, is that pretty close? Yeah, it's a little higher. Slope is 194. And then you've got your 2 separate intercept points for male and then for female. Remember, again, it's additive to the base value. So a male on average makes $37,000. And then a female on average makes $37,000 minus $22,000. And for the last one, we've got a different slope for the male and the female. Okay, so let's think about how to interpret this. I'll just really quickly draw this so that we can have it in our minds. You've basically got age and then two lines. And similar to the way where we have a base value and then another value, you're sort of doing the same thing for the slope coefficient. So if we look just specifically at the graph, right, there are 2 parameters that define the line. You've got your slope and your intercept. And so now we have essentially 2 different lines, 2 different slopes, 2 different intercepts. So we're going to need these 4 parameter values to define essentially the characteristics of both lines. So the based value is the easiest one to interpret. It's just it's just as written, right? And so the base value is for the male, and so our intercept for male here is 28,654. So this point right here would be 28,654, and then our slope is 394.88. So the rise over run would be for every year. For every year they're older, then they make 394.88 more. And for the female, okay, we've already discussed that the base value is for the intercept is 28,654 minus 7,651. So this point here would be 28,654 minus 7,651. Okay, and then the tricky part is we have to do the same thing for the slope. It's minus 324.69. So it's not a slope that's negative 324. It is 394.88, which is the male one, minus 324.69. Okay, and so That's essentially how we go about interpreting the interaction variable. When we go from dummy variable to multiple categories, it's treated in the same way, except you may have multiple other levels besides this. In fact, I can just go ahead and show it really quick. You may have something like this. So age plus race plus age times race. And if we look at a summary of this, you now have a base race, which in this case is black. Again, it starts with, it just goes in alphabetical order. So you have black, Hispanic, other, and white. So black ends up getting set as the base level. And then you have each of these races here that are indicating different intercepts. And then you have different slopes that are differentiated from age. The age and the base. So this is interpreted in the same way, right? So for our base, it's saying that on average, the black will have $19,000 intercept with $213 increase per year of age. For someone who is Hispanic, they will make $24.90 higher at the intercept at an age of 0. But every additional year in age only is 213 minus 118, and so on and so forth. You essentially use the same rules to make the interpretation for both the intercept for each of the races and for the slope for each of the races. Okay, so if anyone is confused, feel free to speak up now. I know that for folks who have done regressions before, this can be pretty familiar, but for those who haven't, it may be a little bit confusing. Definitely work through this on your own if it's not clear, and see if you're able to basically interpret what the coefficients mean among different combinations of the continuous variables and your categorical variables and combinations of the interaction variables. This will be the interpretation of these sort of models will be one of the things on the next homework, which will be available after the end of class today. So do make sure that you understand this. Okay.
Yeah, Alan, I had a quick question on the interaction variable.
Yes, go ahead.
Yeah, so when we analyze a particular data set, so as someone who's analyzing the data, should we know inherently that some variables might have an interaction, and that is when we decide to run a particular model with an interaction, or we just check with different selections of variables just to see if there is an interaction or not?
Yeah, that is a really good question, and actually a pretty good, I think, segue into a whole slew of topics that we're going to be talking about in the next couple lectures. And that's having to do with model selection. So kind of beyond just talking about the interaction of variables, there's this question of, okay, we've looked at how to so we looked at how to interpret variables. We've looked at how to roughly diagnose whether the model fit is okay. And now there's this question of, even here, looking at wages, right? I have height, sex, race, education, age. I have these 5 different variables. Um, how many combinations of variables are there? What is it? Is it 5 factorial? So 5 times 4 times 3 times 2. So yeah. So you, as you sort of marginally add more and more variables in your data, your combinations for possible variables kind of explodes pretty quickly. And so there's this question of how do we go about determining um, which variables to put in our model, which ones end up making the model sort of the best as possible. And so we're actually going to show explicitly some statistical techniques to try and do that. Regarding specifically the question of interaction variables, that one is a little bit trickier. So yes, you're definitely, I think the best one is kind of your intuition about whether or not the combination of 2 variables, like qualitatively, makes sense as an interaction, right? Because you might imagine that like education and race, for example, the combination of those 2 things, you might be something that you want to test out. And so oftentimes that is how people end up deciding to test specific variables. And the reason why some of the techniques that we'll be talking about in future lectures are kind of less suited for interaction to test out all the combinations of interactions is because there are some simplifying assumptions in how we look at combinations of variables simply because the quantity of combinations increases too quickly. And so the same thing can be said for interaction variables, right? As I add more and more variables, you essentially have exponentially growing combination of interactions to test. And that's why usually when we talk about interaction variables, it's related to things that you suspect are related and want to explicitly test rather than having like a statistical strategy to isolate interaction variables. Does that make sense?
Yeah, thank you.
Yeah. Okay. Does anyone else have any questions?
I have a quick one. Just to be clear, with the summary we're looking at right now,
Yep.
Does the other race have a slope of 213 plus 170?
That's right. So, okay. So why don't I sort of go ahead and quiz you? I'm going to put you on the spot here. So let's interpret the line for the other race. So what would so tell me what the slope and the intercept would be for the other race.
So the intercept, I would say, is 19,000 minus 4,700.
Yep, exactly.
And then the slope would be 213 plus 170.
Yeah. That's exactly right. And one of the things that you can do is even qualitatively by glancing through a table like this, I'm able to quickly make some like qualitative interpretation, right? So I can just say, for every additional year of age, compared to someone who's Black, a Hispanic, both Hispanic and white people make less as they get older relative to someone who's Black, whereas other races make more. right? And I'm looking specifically at the intercept there. But then you could say something like, but they also would start lower, right, for others, whereas Hispanic and white both start higher than someone who's black. Okay, and then I see another question in chat. So regarding the dummies, let's see. In regression analysis, for example, if you have 3 income dummies, should I include all the dummies, or can I include on any one of the dummies and not include the others? Okay, so you would I would more sort of categorize that as a categorical variable. I mean, sometimes they get conflated because it's like subsets of the other, but essentially it's essentially a categorical variable with 3 different levels, and to properly put this in. So if my let me just write this out. So if my variable were in this example, what he's saying is income with 3 levels, low, middle, high. Okay, so the way that we talk about putting one in is, or including this in the regression, is essentially leaving one out so that we don't have a singular matrix. So I might leave out high, I might leave out middle, or I might leave out low. And then you would have essentially two levels to interpret in your regression output, which would look something like this, except instead of 3, it would be 2, and then your base level would be the other one. So if you were to hypothetically just include 1 instead of 2 and leave out 2, then let's think about what that interpretation would be. I think that, again, the way that you would interpret this is going back to the table where you would have low, medium, high, and then suppose it was like 0, 0, 1, 0, 1, something like that. And then you had maybe something that looks like this. Let's see, 0, 1, 0, 1, 0. If I were to leave both the middle and the high out, you are effectively creating a different sort of variable that might look something like this, where it's a combination of middle and high. So even if this isn't what you're intending to do, I think if you left out 2 variables and just put in 1, you're effectively creating something that looks like this. And in the interpretation, your base level would be a representation of the combination of the 2 and then the one that you included. So I don't know if that's exactly what was being asked in the chat, but excluding just a subset of everything would kind of artificially create this like combined variable. So it would be, the way I guess that you would think about it is like you would have, instead of low, medium, high, it would be low and not low. Okay. So that, I think, wraps up the sort of final set of stuff that we'll be talking about with our linear models in terms of interpretation and representation of different types of variables. And so I guess this would be a good time for a quick break, because we'll be moving on to a slightly different topic. So why don't we reconvene at 11 and we can have a quick break. And in the meantime, I'm happy to take any questions okay, actually I see something in chat already. Okay, in this case, okay, so if we look at the summary p-values, there's no significance for all the races and ages. So there's no effect for these variables. Should we pull them out of the model since they're not significant? Yeah, okay. This is actually going to relate. This is a good segue again. This will actually relate to the next topic. So in this particular case, you know, I wasn't trying to dive into getting the best model possible. It was more of like doing the interpretation, but sort of duly noted that there isn't any significance, which is indicating that our coefficients are not statistically different from 0. And then there's this question of like, okay, does that mean that we should pull the variables out of the model? Well, actually, let me. So first of all, I'll say that pulling out models based off the significance of the variable is something that for some reason has been propagated in some statistics classes where people are I think teaching how to do like stepwise regression incorrectly, and generally it's not necessarily a good practice. Just because a variable isn't significant doesn't necessarily mean that it doesn't belong in the model. And actually, I wonder, I'm not sure if this is quite the case here, but I wonder if I can demonstrate this. I'm just going to test something out. Yeah. Suppose you look at this model and you say age isn't significant, so I'm just going to pull that out. But if I were to run a regression with just age, it is significant. So what does that mean? Am I supposed to include it or not include it? Or if and you might run into this issue where you look at that first model and then you pull out age and you think now you're good, but that if you ran it alone, it's clear that age does have some sort of influence. And let me go ahead and do it this way. So instead of age, I'll just put in race. And in this case, maybe you see that race isn't significant. Well, there is maybe a slight difference here at the 10% level. So if you went in that direction, maybe you'd be more okay. But generally, you can see that there's this issue where the additivity of influence of variables on your outcome may not be linear, and in some combinations they may make sense. So yeah, I would say we're gonna look at a bunch of tools that are gonna allow us to think about how to put variables into the model in ways that are better than just looking at the p-value. There's actually a fair bit of like literature and discussion about why when you do something like a stepwise regression based just on the p-values or sorry the standard errors and the significance and the probabilities, that you end up biasing your model towards variables, towards specific types of variables that look significant. Whereas the real effect, even if it's not significant, may have an influence on the model in ways that you want. Okay, so sorry, that may have been a pretty long-winded way of saying that you shouldn't just pull out variables just because they're not statistically significant. That's really not a good practice. All right. Let's go ahead and move on. So one moment while I get my notes organized. So the next thing that I'm going to be talking about is somewhat related to some of these questions that have come up. Thinking about model selection and also having to do with model validation. And so we're going to look at a, I think, pretty commonplace test that takes place in a lot of statistical models it's kind of my go-to validation protocol. So, okay, let's go to the whiteboard. So let's kind of take a step back and think about what we've covered so far in terms of thinking about the quality of a model. So there are things like the statistical significance related to the standard error, right? Which is kind of telling us, well, there's this thing about whether or not your slope, your coefficient is different from 0. We've talked about R squared, where we're looking at the difference, or sorry, the amount of variation that our model is explaining. But I guess in my mind, and maybe this is more of a personal thing, you know, when I think about running a regression, we are trying to relate our explanatory variable to a response variable. So as things change in X, we want to see how things change in Y. And ultimately, I think one of the best measures for how good a model does is essentially how well my X actually predicts my Y, right? So regardless of my, R squared and whether or not things are significant, if my X's predict my Y's really well, that tells me something about the quality of the model. So this is the case even for, understanding like causal relationships, where it's like not necessarily all about getting prediction, being robust in determining the relationship between the X and the Y. You still want that relationship to be representing something real, right? And so that's something that we are now going to try and focus on. So how is it that we can do a validation of our X's on our Y's? So we've talked about mean squared error, right? And so let's do a quick refresher. So you may have a line that looks like this, and the mean squared error is essentially looking at the difference between the sort of average difference between your line and the actual data points. And if we look at a different line that looks like this, you may actually be able to find a model with a better better mean squared error, right? And so maybe in this case, the red line might look better than the black line. But in fact, you could, in theory, continue to, for example, add variables into your regression until you get a perfect fit. This relates to explaining the variation through the R squared by sort of throwing more and more variables. So let's say the red line has a better mean squared error than my black line. Well, I can show you a quick way to have an even better one, a line that has a better mean squared error, right? And so this green line that I just drew has a mean squared error of 0. Okay, because the line goes through every point in my data. And so at what point are you sort of going too far, right? So I think one way to think of this conceptually is what happens if I were to kind of think of this same procedure where I have a whole bunch of data points and I want to fit stuff through, but I don't want to do what's called overfitting. So the way that you sort of deal with overfitting is to validate against data that wasn't used in training your model. So in this case, let's say I have all of this data here, but I also have, let's say, it can be a whole set of additional points in blue. So let's draw a line like this, which is one type of fit. And then maybe you could draw your other crazy green line like this. And now, so we've trained both the black line and the green line against the black dots, and then we have extra data, these blue dots. And it may turn out that with all of these extra points, that the black line ends up being better when you compare it to a set of data outside of what you trained your model on. And that's because the green line has overfit the data, and any additional data that you try to put into it would do a really poor job of fitting. And so, okay, so hopefully folks can understand kind of the difference that's going on here. So now you might ask, okay, where are these blue dots coming from, right? Generally, when you have a data set, you want to be able to run your model against as much of the data as possible. And so you may not want to leave out all of the data. It may make for a slightly worse model. You know, so sometimes there will be, in rare instances, you may have like separate data sets where you have something to train on and something to test on. But that's that's not all, sorry, that's not always the case where you have data that's like separable and easy to deal with like that. Okay, and so how can we go about trying to do this particular procedure? There is a concept known as cross-validation, which essentially lets you do this. Okay, actually, before we get there, I've been saying this thing about training set and testing set. So one way that you might put this is if I have a training set, this is essentially what I use to calibrate the model. And then our testing set, so these would be our blue points. So the training set are the black points, the testing set are the blue points, and they are not, so when you calibrate your betas or you calibrate your model in any way, and you estimate the coefficients, you are not using any of the blue points, you're only using the black points. So the testing set is the thing that helps to diagnose model. And you can have some kind of feedback loop that looks like this. Yeah, so again, this is kind of an idealized situation. Testing data sets are not typically available, and if they were available, why would you not just include, so why not just include all those blue points in the training set in the first place to better calibrate your model? So this is where we run into what's called cross-validation. So this is a neat little device that lets us generate a testing data set from our full data set and yet still allow us to sort of calibrate the model, taking advantage of the full data set. So essentially what we're going to do here is, if we have our full data set, we can break this out into, actually, I'll draw it like this. Maybe it'll be clearer. So this is our training data. And then we take a piece out of that as our testing data. Okay. So this is, this whole idea of having training data and testing data is this idea of doing what's called out of sample testing. And out of sample just means that when you do validation of your model and testing of your model, you're using data that wasn't initially trained on. And that's the thing that's going to let you sort of overcome the overfitting issue. And we're going to talk about this in a little bit more detail, but you can imagine that if I add more variables, then let's just call it sort of a generic sort of model goodness. So in sample model goodness is going to increase. And the same would be happening for the out of sample. So as you add more variables, the out of sample model goodness may also be increasing to some extent, but at a certain point, you're going to start overfitting, and then the goodness in the outer sample will sort of decrease. Again, this is kind of just introducing ourselves to the topic. We're going to be talking about this in quite a few future lectures and showing, I think, more visual examples. So don't worry too much if this is a little more confusing at this point. So I'm going to talk about the procedure to do a specific type of cross-validation called K-fold. So CV, which we stand for cross-validation, we're going to look at an example of implementing this with what's known as K-fold. Okay, so I'll sort of walk through the steps of how to do this. But before I do that, we'll sort of describe qualitatively what's happening. So in this procedure where I divide this into, like a big chunk and a small chunk, like this, essentially what you want to do is to run your model against our training set and then look at the mean squared error of your K-fold. So you're going to predict, you're going to look for your y hat and then calculate your mean squared error. So again, to back up and think about what this is doing conceptually, you are essentially looking at how well your model predicts your outcome using quote unquote out of sample data that you've carved out of your training set. With the K-fold though, one of the things you might worry about is that, oh, what if it just so happens that this random selection of data that I've pulled out of my main data happens to like look really different or look kind of weird. And so to be robust about this, you repeat this a K number of times. And so this, we're going to not only run this procedure, we're also going to do it like this. We're going to cut out a different set of data, and we're going to cut out another different set of data, K times, right? Okay, and just to distinguish, right? So this would be like, so you're grabbing different pieces of data from your initial training set. Okay, so the algorithm to do this, I'll sort of just write this out. So divide data into K subsets. Calibrate. Okay, I see, hang on, there's a question here. Will those test sets be part of the training set while creating the model? Yeah, so you will, you're going to run it in essentially a for loop. You take out one piece of the training set. So let's see, if I were to just kind of quickly show how this would work. So this might be like A, B, C, D, E, F. 1, 2, 3, 4, 5, 6. 6, 5, 4, 3, 2, 1. Essentially, the first step would be, suppose I cut out this thing. So that's my test. That's my test set, and this is my training set. So I'm going to run a regression. Y equals beta x1 plus beta x2, so beta 1, beta 2. And then I'm going to calculate y hat for x1 and x2 using the estimated betas from here. And then you can do the mean squared error as a function of your y hat and your y. Yeah, maybe, hopefully these colors help out in sort of just distinguishing what's going on here, right? So then you can see how close to E and F you're getting based on a model that wasn't trained on calibrating to E and F. So you're explicitly avoiding overfitting. Okay, I'm just gonna make a new page and sort of write this again. Okay, so 1, divide data in k subsets. 2, calibrate model on all but one subset, which is going to be our training set. 3, predict y hat on the subset of data left out of calibration. And then calculate mean squared error based on out of sample prediction. And then repeat process, leaving out a different subset. Different subset each time until all k subsets are done. All right. So, yeah, I guess I've been explaining this a couple different ways, and it is kind of a complicated procedure. So if you're not quite there right away, do make sure to review this, because this concept will be pretty important for the rest of class. Okay, there's a question: how big do the testing subsets need to be? Yeah, so you typically evenly divide the data in a k-fold. So if it's a 5-fold, so if k equals 5, then you are dividing your full data set into 5 pieces. So each subset will represent maybe 20% of the full data set. There isn't a hard and fast rule for how many folds you should do, but typically I run something between like 5 and 10. And so you're usually working with chunks of your data for testing like 10 to 20% of the data. And of course, that's going to kind of depend on like the size of your data set. You know, if you only have like 20 data points, you probably want to do like less folds. sorry, you wanna like leave out as little as possible for your calibration. So you might want to do something like maybe a 10-fold, so that you're leaving out just like 2 points at a time, something like that. But as you have like 20 million, as you cut out large chunks of that data, you have plenty more to work with. So your number of folds can be smaller, but I wouldn't necessarily go, anywhere too much below like 5.
Alan?
Yes.
I was just gonna ask, so what's the end product for this is then like a summation of the mean squared errors, or what do you try to get out of this?
Yeah, you would. Yep, exactly. So you're going to end up with, like if in a 5-fold, you'll end up with 5 mean squared errors. So you could run, or you could take the mean of those as a general metric. Okay, and so what is the use of this? So let's say you're debating between looking at a model like y equals beta 1 x1. You're looking at beta equals beta 2 x2. You might have or y equals beta 1 x1 plus beta 1 x2, and maybe you have something like beta 1 x1 plus beta 3 x3. Okay, and you have a bunch of different models and you don't know which one is kind of the best. Well, because you're actually using the same explanatory variable in this case, what you could do is go through this procedure with all of these different models and basically look at which one predicts the best out of sample, right? And by comparing the average mean squared error coming out of your k-fold for each model, you have a direct comparison, like a really direct comparison of like how each of these are predicting the y's relative to each other, and that's generally a really sort of quite robust way of getting a good model. Yeah, go ahead.
I have a question kind of along these lines, but so if you calibrate the model each time on the different set of data without that one k-fold, you're going to have 5 different like B values.
Yes, exactly. No, you're going to have 5. You're going to have 5 different mean squared errors, and you kind of just take the average of those. And okay, wait. I see what you're saying. Your coefficients are going to be slightly different.
Yeah.
But this is more testing the quality of your model specification. So you don't end up using the betas from an individual k-fold training. This is a good point. You end up saying this model gets the lowest average mean squared error out of all the ones that I've looked at, and so I'm going to go with this one based off of my validation. And then when you do the final calibration, you just use all the data, right? Because you're confident that that's already the one that's doing the best prediction. So then your betas are also as robust as possible because you're calibrating to all the data. Does that make sense? So you do end up you do in the process of the k-fold have like 5 different betas, but then for the final one you end up choosing this model and then just using calibrating against the full data without leaving anything out, and then using those betas.
That makes sense. Thank you.
Okay. So let's look at how to implement this in R. So I think it's kind of handy to, so first of all, I'll say that a ton of the functions that we're going to look at, obviously, cross-validation and k-fold validation and different versions of k-fold validation are pretty commonplace. A lot of people use them. It's a robust tool. So there are most definitely built-in functions to do this. Actually, not so much in the linear models. When we get to more non-parametric and semi-parametric models, that's a lot of when they'll show up. And so we kind of do have to do this initially to do k-fold for linear models. And essentially what I'm talking about is making the cross-validation with our own custom function rather than using a built-in function. You know, a couple good reasons, good practice in R, and it also, by knowing what the function does in the code, it'll really solidify what's all this going on in your mind. So we're going to walk through this in the code, and this is definitely something, again, that I would encourage you to have a firm understanding of. Okay. Let me make sure we don't have any questions in chat. Okay, good. Let's do, okay, so let's make a function called k-fold. We can walk through this step by step. And in this case, we are going to, let's see, we are going to do this for our wage model. So the input is going to be our initial set of data, and then the number of folds is how many times we're going to do the iteration by leaving out training and testing data. So there's a whole bunch of different ways that we can do this, and it doesn't have to be the way that I'm writing it out. There are more sort of creative ways, and probably I can already think of slightly abbreviated ways, but hopefully the way that I'm going to write this out will be a little bit more clear for interpretation. Here, I'm going to create an index, and that's going to be sampling from 1 to the number of folds. So suppose this is 1 through 5. It's just going to draw numbers out of a hat that could be 1, 2, 3, 4, or 5. And it's going to do that how many times? I'm going to do that equal to the number of rows in my data set. Okay, so if my wage, let's see. So my wage data set has 1,379 points. So it's going to draw the number 1, 2, 3, 4, 5 randomly out of the hat, 1,379 times. Obviously with replacement, otherwise you'd run out of numbers after 5 draws. And I'm just going to create an extra column that is saying that has a corresponding index number. So essentially what you can imagine in this table is there's an extra column here called index, and it has randomly a number 1 through 5. And we'll assign that like that. I'm going to create a little bucket here called mean squared error all, and that's just an empty placeholder that's going to be holding the mean squared errors that I'm estimating in my model. Okay, so I'm going to run this procedure a total of 5 times. So it's just 1 through 5. And I'm going to, as it runs through, right, it's going to, this n value is going to be 1, and then it's going to be 2, and then it's going to be 3, all the way up to 5. And now I want to create a training set of data and a testing set of data inside each iteration of running through the k-fold. So my training data is just going to be my input, but it's going to be a subset of my input, right? So it's going to be this wages data right here, except I want to leave one index number out. So in this case, I'm going to leave out index number 1, and then the training data will be all of the data where each row index is either 2, 3, 4, or 5. Okay. So here it would be input dollar index does not equal to n. Okay, so in this case, in the first iteration, n is equal to 1, and I want everything from my input data except where the index is equal to 1. And that's because my testing data is going to be the thing where I include the index equal to 1. So now I've essentially separated my input data into these 2 sets. And actually, you can imagine that as I run through this for loop, it's going to continue to create different training and testing data based off of that index. Cool. Okay, and so the rest of this is kind of procedural, right? We're just training our model, calculating the mean squared error from our prediction. So I'm going to create a model. I'm just going to call it model hold. That's kind of my go-to variable. I just call everything hold for a temporary variable. So we're going to do earning of height, sex, race, education, data equals training data. Okay, so let's look again at what this does. So our linear model, regressing earnings on height, height, sex, race, education. And before we had been putting the full data set. So normally you would put like data equals input or data equal wages here. But instead we are only calibrating our coefficients to our training data, and we're leaving out the testing data. And then we want to generate our predictions. So these are our y-hats. Predict, model, hold. Okay, I realized that I don't think I ever talked about this. When you do a prediction, so that generating the y-hats, you can actually put in new data. And the default, if you just do prediction, is it's going to predict on the data that was used to calibrate the model. But we don't want to do that in this case. We want to predict on new data. So the way we input that is we just say new data equals, and then whatever we put here is the thing that it's going to be training on. So just keep in mind that when you have this particular input in this function, whatever you're putting in for new data has to be in the same structure as your initial data in your linear model. So it has to be the same data structure as the thing that's being put in this data here. Or at the very least, it doesn't have to be exactly the same, but it has to be like a data frame or a data table that contains columns with the same names. Okay. The new data can technically include other columns, but it won't look at that. It just has to have the same name so it knows what to do the prediction on. So here, right, we're not doing new data equals training data, we're doing new data equals testing data. So this is going to give us the y-hat for predictions essentially of our model that's been fit to the training data using the testing data. So this is an out of sample prediction. The mean squared error we know is the mean of the difference between the actual points, which is the wage dollar earn, or in this case from the testing data dollar earn. So that's our actual y, and then minus y-hat, which is our predictions. And then we square that for mean squared error. And the last thing I'm going to do here is I'm going to put that into my little bucket that's going to hold all of them. So here, this is a handy little coding trick for those who are less familiar with programming. Oftentimes, to hold onto objects as you move through a for loop, you can essentially append onto the previous one. So in other words, let's say the mean squared error as I go through the first one is 1, and then the mean squared error for the next one is 2 and 3, and so on and so forth. So what this bucket looks like, MSE all, before I get into my for loop, it's just nothing. It's empty. Okay, when I get to the end of my for loop, it's going to look at, it's going to redefine MSE.all as what existed before, which was nothing, appended to the first MSE hold, which I said was 1. So now you jump back to the top of the for loop and you go back through all this, and then you hit MSE all again. And then now our MSE all is defined as 1. The next one is 2. So now MSE all is 1 and 2. And then you move through and it continues to append them on. So you'll end up with an output of five MSEs for a k-fold of 5. So I'm going to go ahead and return MSE.all. So if I go ahead and run this, we can now look at what happens in our k-fold. So k-fold, and I'm going to have wages as our input data, and number of folds can be, let's see, we'll say 5 folds. And so this is our set of mean squared errors. If you just wanted to get 1, you could do that. Not MSE, mean. So the average of the 5, and that would just return 1 value. So if I run this and go ahead and run my k-fold on wages. Okay, so I'm running this a couple times, and we can actually see there's a little bit of variation. So who can tell me why the number is changing? Anyone have any ideas?
The predict function kind of draws a different y-hats each time you run the model.
Yeah, in fact, it's because, well, it's kind of related to that. That's exactly right. But I guess the base reason for that is that our testing and training data are randomly selected. Okay, and so because of that, you're going to get variation in the mean squared errors coming out. And that's why you have a difference. I'm going to call this k-fold 1. Let's make another k-fold, oops, to now actually do a proper comparison. So let's say I wanted to investigate a different model, and I wanted to look at something where I didn't include, for example, the race. Okay, and so now this is we're gonna formalize this procedure in the future, but essentially what's happening here is now I want to compare essentially the predictive ability out of sample of a model that has those first all four variables versus a model that has only these 3 variables. And I can do that, oops, by looking at this. So we've run k-fold 1 a couple times, and now let's run k-fold 2. Our input data is wages, and the number of folds, we'll keep the same number of folds to be as consistent as possible. And so I can run k-fold 2 a bunch of times, And you can see here that the predictive ability of this particular model appears to be somewhat similar, right? We looked at the ranges. But what if, okay, let's make the model, you know, particularly bad. I think hopefully if we do this, it'll be worse. Okay, so in this case, right, if I compare this against k-fold 1, you can see that the mean squared error from the first model compared to the second model is quite a bit lower, which means our predictions are better, right? So lower mean squared error is better than high mean squared error. And of course, it's kind of clunky to be like changing the model in the function. Normally, you would want to have that if that was an input category that you were interested in, you could have that as out here, but it's a little bit trickier. And I think actually if I remember correctly, that one of the problems on the homework is to turn this function into a generic version where you can do for a linear model any treatment of y's and x's. So again, it'll be really important to really understand what's going on here. Yeah, okay, and so this particular tool is going to be one of the primary diagnostic devices for in-sample and out-of-sample testing. It's not going to be the only one that we use, but the procedure here and the sort of general principle of testing your model against data that's out of sample of the thing that you've calibrated is kind of opens up the world for us to think about different ways of approaching how we put our model together. And we're going to see lots of different ways we can exploit this in coming lectures to not only diagnose our model, but to help with things like model selection. Okay, so I think that's all we're gonna cover for today. I'll definitely post these notes right after class, so you'll be able to look at this and review it if need be. This concept will be appearing on the next homework, which should be coming up. I think it should appear in Canvas in 10 minutes or so. And so the next homework is going to be due on the next Thursday, so a week and 2 days from now. Okay, so we'll end here for today. Unless there are any questions, I'll stick around for a couple minutes.
Yeah. Hey, Alan, I had a quick question on your coding for finding the index. So
Yes.
what you're doing is you're taking a random sample and then why did that end row come up?
Yeah.
Yeah.
So sample 1 to 5 is essentially what I'm doing. So if I do this, if I have 10, oops, I have to do replace. It's true. Then it's pulling 1 through 5 out of a hat 10 times. Okay. So that's what the second input is. So this end row is saying I want to draw 1 through 5 a number of times equal to the number of rows in my data, so that I can assign a new column called index that will have 1 through 5, 1379 times. Does that make sense?
Yeah, got it. Thank you.
Alan, I have a question.
Yes.
So you decided, or in the procedure for doing k-folds, you used MSE, but could you use other metrics like R squared?
Yep, absolutely. And actually some of the procedures we're going to look at will do a similar type of thing, but not just with MSE. So in fact, that R squared or adjusted R squared, AIC, BIC, there's a couple different metrics that we'll talk about in the future and to fold into out of sample testing that are commonplace in certain types of validation tests. My go-to is the mean squared error, but that's kind of like a personal preference. Also, it's kind of what I was taught, and it's used a lot. But there are definitely other metrics you could put in there for sure. Okay, there's another question. Okay, this is specific to the code. Okay, so for this question, I would say we can look at this independently. I think that make sure that you are copying the code exactly. It looks actually even like what was pasted in the chat might be. I think you're supposed to do. I think you have a tilde instead of a subtraction. At least what you've pasted. So make sure it's a minus, not a tilde. If that's still not working, you can you can shoot me an email, but I'll post this code and you can copy and paste it and then compare it against what you had written down.
I have a question, not specifically about this, but going back a little bit to some of the plotting stuff that we did a couple of lectures ago.
Sure.
So with things like ggplot, you said that it prefers to have data in a long format.
Yep.
Because when you specify your plot, like you might say, you know, your x is a single column, and then it's looking in that column to get the different x values.
That's right.
If your data is kind of, instead of having your x values in a specific column, you kind of have it a little bit wider, and like each x value is a different column, and you have the values in that column. Do you have to melt it to get it into long format, or is there a way to work with it in that kind of wider format in ggplot?
Yeah, let me go to a whiteboard. Yeah, so let's say let me think of an example. Let's see.
Well, I have a data set, for example, where I'm looking at data related to different power plant fuel types. So I had a column that was like natural gas and coal. And then
Okay. Yeah. So let's look at that. So let's say you have generation, and then you have so okay. Let me put this over here so I can show. So generation, and you might have something like so natural gas, and then coal, and then let's see, nuclear, and then maybe you have like something like this. So time 1, 2, 3, 4, 5, and then natural gas. A, B, C, D, E, F, G, H, I, J, K, L, M, and O. So this is what it might look like for a wide format. And then, and so, okay, I know you know this, but I'll just kind of write this out and then we can do a comparison, right? So this would be So 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, so on and so forth. A, B, C, D, E, F, G, H, J, K, and this would be nat gas, and then coal, and then nuclear, and so on and so forth. So that's wide, and this is long. Okay, so your question is, when you do ggplot, essentially, well, you could do something like ggplot and then geom point, right? So if you wanted to look at them individually, you could just do AES x equals T, y equals nat gas. And then you would do one sort of separately for this in a wide format. So it's possible to work this in, except, and then in here you could also explicitly define the color for all the points related to natural gas, and then a different color for all the points associated with coal, and kind of so on and so forth, right? And so does this kind of make sense for how you would think about implementing it in a wide data set?
Yeah, so basically you have to specify a different geometric, like whether you're doing point or like bar graphs or whatever else, you have to specify as a separate.
Yeah, and that's essentially, it makes sense, right? Because you're essentially saying, like, you're basically telling it over and over, here's my X and here's my Y. And because you've organized it in different columns, you're saying, well, okay, I also want you to graph this as a Y, but in any software, you would, in data organized in this way, you would have to point to that as another Y, right? So it's not as though it's like more tedious than any other way that you would do a specifying X and Y in some kind of plotting software.
Yeah, that makes sense.
So that's kind of why I suggest doing it in the long format, because if we think about it, ggplot, I don't know why it switched to green. I think my hand hit the button. Now it's X equals T, Y equals gen. And then if you were separating them by field type, you could just add color as an entirely like grouped subset field type, instead of having to say color and then pointing it out every single time. You know what I mean? So the benefits of like having your data organized into long just makes life more convenient in ggplot.
Would you gain any extra control over each of the categories like field type if you specify it in the wide format and specify different geom points? Or like if you wanted to specify specific colors or specific aspects of each one? Or I'm sure there's probably ways to do that in the long way too, like if you pass in a list of colors or something.
So you should, in theory, be able to do everything in the long format that you did in the wide format. And so you're right, there are like other ways where I could explicitly specify like colors in the list, but to be equivalent to wide, all I would need to do is this. So same thing where I would have multiple things to control. And then you would just say, suppose, oh shoot, what did I do? Okay. Suppose the data set is called generators, or gen for generators. Then you just need to subset this to fuel type equals nat gas. And then you do your AES for your X and your Y, and it's only going to look at this subset of data here. So it'll look exactly the same as if you had it in a wide. And then for other ones, like we were saying, that you do separately, you would do the same thing, but data equals like coal or something like that.
Okay, that makes sense. Thank you.
Yep, no problem. Okay. Oh, I guess a bunch of people stuck around for that. Any other questions before we end for the day? Nope. Okay. Well, thanks everyone, and we will continue on Thursday. I'll see you guys Thursday morning.
Thanks, Alan.
Mm-hmm.